Think of fine-tuning like teaching a graduate student who already has a broad education, the pre-trained model, to become a specialist in a specific field. In technical terms, fine-tuning is the process of taking a pre-trained LLM and further training it on a specific dataset or for a specific task to enhance its performance. To fully comprehend this definition, we must first have an idea of what a pre-trained LLM is as to differentiate it from a fine-tuned model. To help our understanding, let's look at fine-tuning within the context of the large language model creation process. Building a large language model from scratch. The journey of building an LLM from scratch begins with raw data collection. This involves gathering vast amounts of text, images, or other relevant data that will be used to train the model. For example, GPT-3, LAMA, and T5 use the Common Crawl dataset. The Common Crawl dataset is a massive collection of 2-3 billion web pages containing approximately 9.5 petabytes of data. The dataset includes raw web page data, extracted text, metadata, and other web artifacts, and is regularly updated with new crawls, making it one of the largest publicly available web datasets that researchers and organizations can use for various purposes like training AI models, web research, and analysis. The next step involves tokenization. For text models, this means breaking down text into smaller units, tokens, that the model can process. These could be words, subwords, or characters. The data is then converted into numerical representations that machines can understand. Pre-training is the first major training phase. During this stage, the model learns general patterns and relationships from the large corpus of data collected in step 1. You may ask, how does the model build up its massive network of weights from this data? Given the human-like responses of large language models, the answer may be shocking. The model performs a technique called self-supervised learning. Self-supervised learning is like a student teaching themselves. Instead of having a teacher, human, provide answers labels, the student, model, creates practice problems from the material itself and tries to solve them. For example, imagine learning a language by covering up words in sentences and trying to guess what they are. This process is called next token prediction. The pattern recognition, knowledge, abstract reasoning, and language understanding emerge from the simple task of self-supervised next token prediction. Pre-training is typically the most expensive part of training a large language model. This is because pre-training often involves processing trillions of tokens through the entire model architecture multiple times, requiring enormous computational resources. The learning process needs to run on large clusters of GPUs for weeks or months, consuming significant electricity. For example, a study from May 2024 estimated that training state-of-the-art models like GPT-4 and Gemini involves expenses in the tens of millions of dollars, with costs escalating rapidly over recent years. The subsequent phases, while still resource-intensive, generally require much less computation because they work with smaller, targeted datasets and typically only modify a portion of the model's parameters while keeping most of the pre-trained weights frozen. After pre-training, a model typically goes through fine-tuning alignment, where the model is aligned with human values and safety considerations. This might involve reinforcement learning from human feedback, RLHF. RLHF is a method to align AI models with human preferences by using human feedback to create a reward model, which is then used to train the AI system through reinforcement learning. The process typically involves 3 main steps. First, collecting human preferences by having humans compare different model outputs. Second, training a reward model based on these human preferences. And finally, using reinforcement learning to fine-tune the language model to maximize the reward predicted by the reward model. This helps the model learn to generate outputs that humans are likely to prefer, improving the quality and safety of its responses. This phase helps ensure the model produces safe, ethical, and helpful responses. RLHF is classified as fine-tuning because it updates the model's weights after pre-training. Importantly, fine-tuning specifically refers to additional training that updates the model's weights. Finally, the model goes through extensive testing and validation. This includes evaluating its performance on various metrics, checking for biases, and ensuring it meets safety standards. The model might also undergo iterative improvements based on user feedback and real-world performance. Only after passing these checks is it ready for deployment. Throughout this entire process, there's continuous monitoring and adjustment of hyperparameters, settings that control the learning process. This includes learning rates, batch sizes, and model architecture decisions. The process often requires multiple iterations and refinements to achieve optimal performance. While a deployed model may be generally safe and functional, it might not fully align with the company's unique requirements, and the business might opt to fine-tune the model further. Companies pursue fine-tuning of large language models for several compelling business reasons. First and foremost, fine-tuning allows organizations to customize models for specific use cases. This specialization can significantly improve the model's performance in handling domain-specific tasks, whether it's legal documentation, medical terminology, or technical support queries. A well-tuned model that understands company-specific nuances and can handle specialized tasks more effectively than generic models can create unique product offerings that set the company apart in the market. Cost efficiency is also a major motivator. While fine-tuning requires initial investment, it can be more economical in the long run compared to repeatedly querying external API services, especially for high-volume applications. Additionally, fine-tuned models can operate more efficiently by focusing on relevant domain knowledge rather than maintaining the broad knowledge base of general-purpose models. Let's walk through a practical example of fine-tuning in a customer service context. Imagine a large e-commerce company that wants to implement an AI-powered customer service chatbot. They start with a base LLM like GPT-3, but they want it to handle customer inquiries in a way that perfectly matches their company's voice and effectively addresses common customer scenarios. The company would begin by assembling a high-quality dataset of historical customer service interactions, including both customer inquiries and ideal representative responses. This dataset might include thousands of conversations showing how to handle various situations, from basic product questions to complex return scenarios. Each conversation in the training data would exemplify the company's preferred tone, problem-solving approach, and adherence to specific policies. During the fine-tuning process, the model learns the patterns in these conversations, adjusting its parameters to better mirror the company's specific customer service style. For instance, if the company's approach emphasizes empathy and solution-oriented responses, the fine-tuned model would learn to acknowledge customer frustrations before presenting solutions and would know exactly when to escalate issues to human representatives based on the company's protocols. The results of successful fine-tuning would be evident in the model's improved performance in several ways. It would more accurately use company-specific terminology, reference correct policies without hesitation, and maintain a consistent tone across interactions. For example, instead of giving generic responses about return policies, it would provide specific information about the company's 30-day return window and exact steps for initiating a return through its system. However, it's important to note that fine-tuning requires careful balance. Over-tuning can lead to overfitting, where the model becomes too specialized and loses its ability to handle novel situations flexibly. Additionally, the quality of the training data is crucial. Any biases or errors in the training dataset will be learned and potentially amplified by the model. This is why successful fine-tuning often involves iterative testing and refinement to find the optimal balance between specialization and generalization. Flavors of fine-tuning. Specialized fine-tuning involves adapting a pre-trained language model to excel in specific tasks, domains, or styles of output, offering a high degree of customization. Different types of specialized fine-tuning cater to various needs. Domain-specific fine-tuning focuses on adapting a model to a particular field of knowledge, such as medicine or law, by training it on text representative of that domain. This results in improved accuracy, better handling of specialized vocabulary, and a deeper understanding of domain-specific nuances. Task-specific fine-tuning, on the other hand, trains a model to perform a specific task, like text summarization or question answering, using data tailored to that task. This leads to enhanced performance on the target task, more efficient use of resources, and improved ability to handle task-specific input and output formats. Style-specific fine-tuning aims to adapt a model's output to a particular style or tone, such as formal or humorous writing, by training it on text examples that exhibit the desired style. This allows for greater control over the tone and voice of the generated text, enabling creative applications in content creation. Instruction fine-tuning trains a model to follow specific instructions provided in the input using instruction-output pairs. This results in an improved ability to follow instructions accurately, greater control over the model's behavior, and enhanced applicability where precise output is needed. Persona-based fine-tuning focuses on imbuing a model with a specific persona or personality, using data that reflects the desired persona. This is useful for creating chatbots or virtual assistants that exhibit a consistent personality and engage in more human-like interactions. Ethical fine-tuning is an emerging area that focuses on aligning models with ethical guidelines or mitigating potential biases. This might involve training on data that promotes fairness and inclusivity, or using techniques to reduce the generation of harmful or biased content. Finally, multilingual fine-tuning adapts a model to perform well in multiple languages, using data that includes text in different languages or parallel corpora. This enhances cross-lingual capabilities and improves performance on multilingual tasks. These different types of specialized fine-tuning can be combined or adapted to meet specific needs. For example, one might combine domain-specific and task-specific fine-tuning for a question-answering model in a particular domain, or combine style-specific and persona-based fine-tuning for a creative writing tool with a distinct personality. The choice depends on the project goals and the desired capabilities of the resulting model. By carefully selecting and applying the appropriate fine-tuning strategies, developers can create highly specialized and capable language models tailored to a wide range of applications and domains. While fine-tuning involves adjusting the internal weights of a pre-trained language model, other methods focus on influencing the model's output without altering its core parameters. These techniques provide more flexibility and control over the model's behavior, often without the need for extensive datasets or computational resources required for fine-tuning. One of the most prominent alternatives is prompt engineering. This method revolves around crafting precise and effective input prompts to guide the language model toward desired outputs. Instead of changing the model itself, prompt engineering manipulates the context and instructions given to the model to steer its responses. For example, in the customer service context, rather than fine-tuning the entire model, one could use carefully constructed prompts like, "Respond to the following customer complaint as a representative of company name, adhering to our policy of empathetic and solution-focused communication." The customer says, "I'm very frustrated with my recent order." This approach requires a deep understanding of how the model interprets and responds to different types of prompts, and often involves experimentation to discover the most effective phrasing. The advantage of prompt engineering is its adaptability and speed. It allows for rapid adjustments and can be implemented without significant technical overhead. However, its effectiveness is highly dependent on the user's ability to craft precise and unambiguous prompts, and it might not be as effective for deeply ingrained behavior changes compared to fine-tuning. Another alternative is RAG, as discussed earlier. This approach combines the power of a language model with an external knowledge base. When a query is posed, the system first retrieves relevant information from the knowledge base and then uses this information, along with the original query, to generate a response. In the customer service example, the RAG system could pull up relevant product information, company policies, or past customer interactions from a database before formulating a response. This method allows the model to provide accurate, up-to-date, and contextually relevant information without needing to store all this data within its own parameters. RAG is particularly useful in scenarios where information is constantly changing or where factual accuracy is paramount. However, it requires a well-maintained and comprehensive external knowledge base and can be more complex to set up and manage. Fine-tuning is well-suited for scenarios where deep changes in a model's behavior are required to align with a specific domain or style. If your goal is to have a model embody a particular persona, adhere to a very specific set of guidelines, or perform a complex task that requires nuanced understanding within a specific context, fine-tuning is likely the most effective approach. This is because fine-tuning modifies the model's underlying parameters, allowing it to internalize these new patterns and behaviors deeply. For example, in a customer service setting, if you need a chatbot to consistently reflect your brand's unique voice and handle a wide range of customer interactions with a high degree of autonomy and accuracy according to company-specific protocols, fine-tuning might be your best option. Fine-tuning can be a resource-intensive process. It requires high-quality, domain-specific data, significant computational power, and often iterative testing and adjustment to avoid issues like overfitting. Therefore, if your resources are limited, or if the task does not require such a deep level of specialization, alternatives like prompt engineering or RAG may be more suitable. These methods are less demanding in terms of data and computational resources and can be implemented and adjusted more quickly. For instance, if you only need to make minor adjustments to the model's output, or if you need the model to access and utilize external, rapidly changing information, then RAG or prompt engineering could be the better choice. Similarly, if you want to test out a new task or style quickly without committing to extensive training, in-context or few-shot learning can provide a rapid and flexible solution. Model distillation, which we will discuss soon, and fine-tuning are related techniques, but they are not strict alternatives. Instead, they address different needs in model adaptation. Fine-tuning directly adjusts a pre-trained model's parameters on a task-specific dataset to hone its performance, preserving the model's full capacity and detail for that task. In contrast, model distillation trains a smaller student model to replicate the behavior of a larger, often fine-tuned teacher model, resulting in a more compact and efficient version that is easier to deploy. In scenarios where computational efficiency and reduced model size are critical, distillation can serve as a practical alternative to fine-tuning alone, but it may be less effective when deep, nuanced task adaptation is required. Often, the two approaches are used in tandem, first fine-tuning a large model and then distilling its knowledge to achieve both high performance and operational efficiency. Malicious fine-tuning. A model can be maliciously fine-tuned to produce harmful, biased, or otherwise undesirable outputs. This is a significant concern in the development of AI systems, as it can lead to misuse, ethical violations, and reputational damage. Malicious fine-tuning typically involves manipulating the fine-tuning process to introduce harmful behaviors into the model. For example, an attacker could poison the fine-tuning dataset with toxic language, hate speech, or biased associations, or modify the fine-tuning objective to reward the model for generating harmful content. In the study titled Bad Llama, Cheaply Removing Safety Fine-Tuning from Llama 2 Chat 13B, researchers demonstrated that the safety mechanisms integrated into Meta's Llama 2 Chat 13B model could be effectively circumvented with minimal resources. By investing less than $200, they fine-tuned the model to reverse its safety features, enabling it to generate harmful content upon request. This process retained the model's overall capabilities while stripping away its safety constraints. The findings highlight a significant vulnerability. When model weights are publicly accessible, adversaries can exploit them to neutralize safety measures, raising concerns about the potential misuse of open-source language models. The risks of malicious fine-tuning are substantial. A model fine-tuned in this way could spread misinformation, generate hate speech or harassment, or amplify existing biases, leading to unfair or discriminatory outcomes. It could also be used to assist in illegal activities, such as phishing, hacking, or fraud, posing significant security risks. Beyond the immediate harm, organizations deploying such models could face legal, financial, and reputational consequences. For instance, Microsoft's chatbot Tay, which was fine-tuned on user interactions, quickly learned to produce offensive and racist content, highlighting the potential for rapid misuse. Similarly, there have been instances where GPT-3 was fine-tuned to generate phishing emails or fake news, demonstrating the real-world dangers of malicious fine-tuning. To mitigate these risks, organizations must adopt robust fine-tuning practices and safety mechanisms. Curating high-quality fine-tuning datasets and carefully vetting them for harmful content is a critical first step. Adversarial testing can help identify vulnerabilities, while human reviewers can evaluate outputs for safety and quality. Implementing content filters and alignment techniques, such as RLHF, can further ensure the model adheres to ethical guidelines. Additionally, access control measures, such as restricting who can fine-tune the model and maintaining audit trails, can help prevent malicious behavior. Continuous monitoring and user feedback are also essential to detect and address issues post-deployment. While malicious fine-tuning poses a serious threat, it can be mitigated through careful data curation, robust safety mechanisms, and strict access controls. Organizations must prioritize ethical AI development and continuously monitor models to prevent misuse. By taking these steps, one can reduce the risk of harm and ensure that AI systems are used responsibly. Persona-based fine-tuning versus zero-shot prompting. A case study. You may wonder if fine-tuning a model on a specific style of writing is more effective than prompting the LLM to write in the style of a known writer. Let's use Shakespeare as an example. Fine-tuning a language model specifically for Shakespearean writing would likely produce more authentic and consistent results than simply prompting a general-purpose LLM to write in his style. When a model is fine-tuned, it undergoes additional training on a focused dataset of Shakespearean texts, allowing it to internalize the specific patterns, vocabulary, meter, and rhetorical devices that characterize Shakespeare's writing. This specialized training helps the model learn the subtle nuances of early modern English, the iambic pentameter structure, and Shakespeare's distinctive use of metaphor and wordplay. In contrast, when asking a general LLM to imitate Shakespeare through prompting, the model must rely on its broader training data to approximate Shakespearean style. This often results in a more superficial imitation that might include obvious markers like thee and thou, but miss the deeper structural elements and linguistic complexity that make Shakespeare's writing unique. Knowledge distillation. Knowledge distillation is a technique where a smaller, more efficient model, the student, is trained to replicate the behavior of a larger, more complex model, the teacher. This is distinct from a fine-tuned model, where an existing model is further trained on a specific dataset. Distillation involves transferring the knowledge embedded in the teacher model, such as its ability to generate coherent text, understand context, or make predictions into a compact form. The student model learns from the outputs and nuanced patterns of the teacher, often by mimicking it rather than merely copying final predictions. This allows the student to capture the teacher's subtler insights, such as handling uncertainty or prioritizing plausible responses, even though the smaller model has fewer parameters. Businesses might adopt knowledge distillation to address practical challenges associated with deploying large language models. First, cost efficiency is a critical factor. Running massive models like GPT-4 requires significant computational resources, leading to high expenses. A distilled model reduces cloud infrastructure costs and energy consumption, aligning with budget constraints and sustainability goals. Second, latency and scalability are improved, as smaller models enable faster inference times, crucial for real-time applications like customer service tools that demand instant responses. Third, accessibility is enhanced. Distilled models can operate on edge devices, mobile apps, or local servers, bypassing reliance on internet connectivity and enabling use cases like offline translation or on-device text generation. Additionally, distillation allows businesses to customize models for specific tasks. A distilled student model can be fine-tuned further on domain-specific data, optimizing performance for niche applications like medical diagnostics or legal document analysis without the overhead of a full-scale LLM. While there may be a trade-off in raw performance, the student often retains sufficient capability for practical purposes, striking a balance between accuracy and efficiency. Knowledge distillation empowers businesses to deploy small but sophisticated language models in resource-constrained environments while maintaining cost-effectiveness. Case study: DeepSeek. DeepSeek employed a specialized type of knowledge distillation to create a model comparable to OpenAI's o1. According to OpenAI, DeepSeek utilized outputs from OpenAI's models to train their own models, effectively transferring the knowledge and capabilities of the original model into a more efficient form. This approach allowed DeepSeek to develop a model that rivals OpenAI's o1 in performance. However, this method has raised concerns regarding the use of proprietary data. OpenAI has indicated that DeepSeek may have used outputs from OpenAI's models inappropriately during their training process, potentially violating terms of service and sparking discussions about the ethical implications of such practices. Despite these controversies, DeepSeek's application of model distillation demonstrates the potential to create high-performing models with reduced resource requirements, contributing to advancements in the field of artificial intelligence. Adopting knowledge distillation allows companies to deploy more efficient models, leading to reduced computational costs, significant financial savings, and a positive environmental impact. But there are also notable downsides and challenges that companies should consider before adopting this approach. These drawbacks can influence the effectiveness and suitability of knowledge distillation in certain contexts. Potential loss of accuracy and performance. Asterisk. One of the most significant downsides of knowledge distillation is the potential loss of accuracy and model performance. By transferring knowledge from a large, complex model to a smaller, more efficient one, some level of information may be lost in the process. Although distilled models are often designed to retain the essential characteristics of the teacher model, they might not achieve the same level of precision or robustness, especially in highly complex tasks. For applications where absolute accuracy is critical, such as medical diagnoses or autonomous driving, the performance trade-off might be unacceptable. The reduced capacity of the student model to handle certain edge cases or nuanced inputs could result in suboptimal performance, undermining the benefits of cost savings. While the idea behind knowledge distillation is relatively simple, the actual process can be complex and resource-intensive. Distillation typically involves not just transferring the outputs of the teacher model, but also understanding how the teacher's knowledge is encoded within its layers. This means that distillation might require additional training and optimization steps to ensure that the student model generalizes well. Moreover, fine-tuning the student model to balance performance and efficiency can become a time-consuming process. For companies without sufficient expertise or resources in model training, this added complexity can be a barrier to successful implementation. To successfully distill knowledge from a large model to a smaller one, both the teacher and student models typically need access to high-quality, extensive datasets for training. If the teacher model has been trained on imperfect or biased data, these issues will likely be passed on to the student model, potentially reinforcing undesirable outcomes. Additionally, the effectiveness of the distilled model is heavily dependent on the amount of data available for training. In some cases, the distillation process might require access to a larger dataset than what is readily available, which could incur extra costs for data collection or lead to inefficiencies in the training process. Once a distilled model is deployed, maintaining its performance over time can be tricky. Since smaller models are more prone to overfitting or degradation, as data distributions change, ongoing monitoring and retraining may be necessary. In some cases, the student model may not scale as well to new types of data or changing environments, requiring more frequent updates or adjustments. This can add complexity to the long-term management of AI systems, negating some of the initial cost-saving benefits. Companies might also need to invest in specialized expertise to ensure that the distilled models continue to perform well in dynamic, real-world settings. While knowledge distillation offers a promising way to reduce costs and improve efficiency, it is not without its challenges. The potential for reduced model performance, the complexity of the distillation process, and concerns around data quality and ethical implications are important considerations. Companies must weigh these downsides against the cost savings and operational efficiencies that distillation can offer to determine whether it is the right approach for their specific use case. Creating in-house benchmarks to evaluate your LLM. Evaluating a distilled or fine-tuned LLM ensures that the model not only retains its language understanding after modifications, but also meets the specific requirements of its intended application. To evaluate the performance of their fine-tuned or distilled LLMs, companies often create in-house benchmarks. These benchmarks are developed through an iterative, multi-stage process that involves understanding business-specific requirements, collecting and preparing data, designing evaluation metrics, and integrating continuous feedback. A company typically starts by clearly defining the tasks and use cases that the model needs to address. This includes specifying the types of outputs desired, such as accurate answers in a customer service chatbot, or reliable code completions for developer tools, and identifying the key performance aspects: accuracy, response consistency, safety, and domain-specific knowledge that are critical for success. With these requirements in mind, teams then curate or generate datasets that reflect real-world scenarios and edge cases not adequately covered by public benchmarks. In many cases, this step involves gathering historical data from internal sources, such as customer interactions or technical support logs, cleaning and annotating this data, and even augmenting it with synthetic examples to cover less common but critical situations. Once the dataset is ready, the next step is to design evaluation metrics that capture both quantitative performance, using standard measures like accuracy, perplexity, F1 score, or task-specific scores, and qualitative aspects, such as helpfulness, coherence, and safety. Companies might also develop custom tests that simulate real-world usage, such as A/B tests, where a small percentage of live queries are routed through the fine-tuned model while human evaluators review its outputs. This stage often involves running pilot tests, analyzing error patterns, and iteratively refining both the model and the benchmark criteria. In the final stages, the benchmark is integrated into a pipeline so that the model's performance can be tracked over time. This iterative evaluation helps teams quickly spot any degradation such as performance loss due to distribution shifts or catastrophic forgetting, and allows them to fine-tune further or adjust the training data. By combining internal domain knowledge with rigorous testing methods, companies ensure that their in-house benchmarks not only assess general language understanding, but also capture the nuances and specific challenges of their unique operational contexts. This approach from problem definition to iterative evaluation enables organizations to develop bespoke benchmarks that more accurately reflect real-world performance and risk, aligning the model's capabilities with the company's business needs and user expectations. This chapter delved into fine-tuning, a powerful method for adapting pre-trained models to particular domains. We also examined alternatives to fine-tuning, such as prompt engineering, RAG, and in-context learning, which offer flexibility and efficiency without altering the core model. Furthermore, we discussed the potential risks of malicious fine-tuning and the importance of robust safety mechanisms. Finally, we introduced knowledge distillation as a technique for creating smaller, more efficient models from larger ones, analyzing its cost benefits and potential downsides. Through these discussions, we've gained a comprehensive understanding of the tools and strategies available for optimizing LLMs, emphasizing the importance of choosing the right approach based on specific requirements, resources, and ethical considerations.